Remember this slide? We are on slide 5. Remember this slide? We showed it in the other presentation, the same one. And I'm gonna draw question marks around this certified seal, because like everybody here accepts that there's uncertainty, right? Everybody here accepts there's uncertainty in abduction and induction, but in deduction, everybody presumes that there is certainty coming from somewhere. And of course, it looks more certain, if that makes any sense, than the other two, right? Because this is a deduction, it comes from the, it goes from the original, it goes from the general to the specific, etc., etc. It's a matter of definitions. Of course, we are sure of it. However, I do not believe this for the following reasons. What you see on slide 6 is an example of a proof. And I picked this exact proof because when we did a room a couple of weeks ago, like a friendly chat room, when we were talking about these things, I think Hiro brought it up. He was asking about the proof of the isosceles triangle criterion, which is if you have an isosceles triangle, it's enough to have two equal sides, so to have equal angles, and it's enough to have two equal angles to have two equal sides. This was proved in Euclid's Elements, of course. This is proposition 5, and this is an English translation with modern notation as well of that proof. Have fun, reading it at home. If you're interested, take a snapshot. Very clever proof, by the way. I must admit, this is not immediate. Like, this is genius. What I do want to do today is not explain the proof, because this is not a math lesson. But what I'm really interested in is to draw your attention to that certified seal, because this is math, right? That there's a certified seal, this is deduction, this is absolutely sure. And look first on those yellow marks that I have highlighted on the proof. The way deduction works, especially back in the day, especially in Euclid's mind, is that you have to deduce theorems, we call them. So after you start from very given axioms or postulates, he called them, and he had something else called common notions, which we'll talk about in a minute. So using those, you can bring those together to start generating new truths, quote unquote, which we'll call theorems. It's new things that you discover, And then this new thing is called theorem 1 or proposition 1, proposition 2, proposition 3. And then whenever you discover a proposition, you can use it to deduce the thing that follows it. So I am on proposition 5. I'm very free to use whatever I discovered before. So you see Euclid here referring to proposition 2 or postulate 2 or proposition 1.4, or you see here in yellow, in orange, I mean, CN3. This is common notion 3. Feel free on your own time to go back to Euclid's Elements and read what his 5 postulates are and read what the common notions are. Things are equal to themselves and all the right angles are equal. And his 5th famous postulate that makes no sense. It's just very complicated language that we kind of translated in different manners, etc. This is not my point again. My point is, if we're looking at these things, what if the proof of one of those things had a mistake? So the proof of proposition 5 relies on proposition 1.4, proposition 1, proposition 1.3, postulate 1. What if something is wrong there? What if I am at theorem 85? Can you absolutely guarantee that we haven't missed anything? What if nothing is wrong? What if nothing is wrong, but instead of writing postulate 2, he wrote postulate 3 by mistake? So he's referring to the proof is perfect, but instead of writing postulate 2, which is what he wanted to write, he wrote postulate 3 by mistake. This ruins the entire proof. This makes the piece of proof in front of me wrong. If I'm a math teacher, and I am, and someone writes the wrong name for the theorem, as they refer to it, it's not like they have to memorize it, no. But as they refer to it in their work, they wrote a different theorem than the one they want to refer to. This proof is wrong. It's just not the case. That postulate 3 does this, postulate 2 does it, yes. So there's a mistake. How can we be sure? Well, we send it to another mathematician to certify it. Okay, what if that other mathematician also doesn't certify, but did not find the error? So that's problem number 1. We can never know that what is in front of us on the paper is absolutely 100% deduced correctly. We have to sit down and check whether this deduction is correct. Just checking for typos is enough to ruin. Just one typo in this whole thing is enough to ruin the entire thing. Okay? Problem number 2, from the same spirit. These common notions that you use, who says they are common? Common where? Common relative to whom? Do we have to pay and agree to your common notions before we get in? Okay, fine, we agree, but you're asking us to pay beforehand. No, this doesn't work. When you want me to agree with you on something, we have to start in the same base. Starting at the same base does not require me to agree to every common notion you postulate. This the feeling of, imagine a mathematical system that says everything I will tell you is an axiom now, to show you where the problem is, because of course we have to agree on certain axioms to start. But imagine a mathematical system that says these 300 lines, they are all axioms, and that's all I want to tell you. These are axioms. My opinions about this theory are the axioms, and you're not allowed to logically speaking, you're not allowed to object because they are common notions, quote unquote. And how do we where is the so now you have certainty because you forced my hand into agreeing onto these common notions? Wow, very intelligent. Like, this is very useful. Where is the certainty? I'm not questioning the fact that we have to agree to axiom. I'm just questioning the fact that people give in to this feeling of certainty that mathematics gives. It's not. It's paid for. We paid for that certainty, and you pay with the price you pay is you have to agree to common notions and axioms that you probably don't want to agree to, or you have other reasons not to agree to, or you just think they are weird. Just like Euclid's fifth postulate, for example. People later on thought it's kind of weird, this postulate that he uses, and they started using others, and they have new theories now. They have other geometries which are arguably more useful if you want to talk about the usefulness. So this is Euclid. This is a very old mathematician. This is very classical. Everybody knows the geometry. Everybody knows the proofs. Everybody's comfortable with it. We all studied it in school. But you will tell me, okay, modern mathematics is different. Modern mathematics has axioms and has logical language, and it doesn't use natural language like Euclid did. He wrote in Greek. Well, probably he and his disciples, but that's a different discussion. Here we're reading an English text. Typos could ruin it. Okay, fine. Let's go to the hard logical math, right? Let's see a modern example, so that we know, right? If it is, mathematics wasn't certain back then. Let's see if it's certain today. So on slide 7, we see the story of a very famous man, one of the most famous mathematicians alive today. If you've heard of Fermat's last theorem, you know the guy. This is none other than Andrew Wiles, the legend, who solved the problem that stayed for 400 years unsolved, despite the fact that it's a very easy problem. Okay? In short, this is the generalization of a Pythagoras theorem. So instead of having x squared plus y squared equals z squared, which is the Pythagoras theorem, which we know that has infinitely many solutions, Andrew Wiles proved that there are no solutions in integers for higher powers. So for power equal 3, power 4, power 5, power 100, power 1000, you cannot find integer solutions for these equations, unlike the case for Pythagoras, which you can find infinitely many because they turned out to be right triangles. Anyway, this is the story of quote-unquote certainty of this proof. So why is it called Fermat's last theorem? Because 400 years ago, Pierre de Fermat, a mathematician, was reading a book on arithmetic. And he started making comments on this book, on this manuscript he had. Now, his disciples, probably from his children or something like that, I'm not sure of the story anymore, but that book ended up being famous because all those annotations that he made on the side of the book, they had guesses. And I'm saying guesses because he never proved anything. Sometimes he would manage, to write some intuition. Sometimes he would take, very rarely, he will take the time to actually prove it somewhere else in a different place. But on the book, he just had guesses. But guess after guess, people started proving them. So it turns out that he was making very good guesses. What are they? What is he making? The mathematician guesses. 400 years ago, we're not judging. We are modern mathematics now. He makes these guesses, and he makes one of those guesses is the what we call today Fermat's last theorem. Xn plus yn equals Zn has no solutions for n equal 3 or higher. Fermat himself claims he has a proof. He writes the famous joke, right? I have a proof, but it doesn't fit in the margin. And then separately, later on, he proved the case for n equal 4. So for the power 4, he managed to generalize it from Pythagoras. So using some relation to Pythagoras, he proved that it's not possible. And then 200 years later, another mathematician, brilliant person, Sophie Germain, she proved the case for n equal 3, n equal 5, n equal 7, which turned out to be very expensive. And then Ernst Kummer, very modernly, I think, what is it, 50, 60 years ago, something like that. More actually, wait, I'm too, 120 years old, something. Anyway, he proved it for all regular primes, right? So if you're not sure what regular primes are, this is a family of primes that is related to this problem. Just click on the link if you're a nerd and you want to find out. Not very important. So until now, we don't have a proof, but people are still guessing, and they're saying, oh, no, that's the thing, doesn't have solutions, they start working on it. All we have is guesses and then proofs for very specific cases. The computer gets us to 4 million. So when the computer age started, we started running these numerical methods to solving this. And it got us up to 4 million. And then some other developments happen as well. And then we reach the place where Andrew Wiles, the famous mathematician, started working on it. He spent like 20 years of something working on it in secret because he was too ashamed to admit that he was working on the problem, because everybody called him crazy for working on it. This is a famously 400-year-old, notoriously difficult problem, right? He ends up connecting and inventing all sorts of new, very modern, very, esoteric mathematical theories, I want to say. Something that has to do with also developments happening in Japan in parallel. He publishes a proof in year 93. Sorry, I'm taking a whole lot to tell the story, but this is the story of certainty, I remind you. Huh? All of this is very certain, absolutely, 100%. He publishes a proof in year 93. An error was found as they review the proof in year 94. He spends like 2 or 3 months thinking about this on his own, doesn't get anywhere, gets the help of his student, Taylor. They sit down, work on it for 7 or 8 months, and then they publish a correction in year 95. And then after that, people visit it again, and they're like, okay, everybody now is happy that Andrew Wiles has the proof. It has been established for around 30 years now that Andrew Wiles, in the second attempt, he got the proof right. This is the story of mathematical deduction and certainty, from Pierre de Fermat to Andrew Wiles making the mistake on the first time. Just to show you again that even with modern mathematics, super esoteric, super precise, super careful, you can still make mistakes. What does this look like to us? Does it look like certainty? Does it look like this method autocorrects? Well, if it does, I have news for you. The scientific method does exactly the same way. People have guesses, they go, they experiment, they refine them, the scientific community looks at them, they find problems with them, they fix it again, they publish, someone else fixes it, someone else uses the result, they come up with something new, etc., etc. Just by judging point number 1, they look very, very similar. In mathematics, it is the mathematician who is responsible to check for the validity of their work, and it is up to us to trust or not trust the rest of the community. And then when a community of mathematicians says Andrew Wiles has it right, it's not up to me to tell them no. I don't know. I must sit down and learn the theory myself. To be frankly with you, I haven't. This is way above my pay grade. And it's above the pay grade of most people. And when they said that there was a mistake, we all believed them. And then when he published his first proof, we all believed, oh, he has the proof. And then when they told us that they don't have the proof, we believed them. And now we believe them. We're taking them face value. Just like what the doctor says. The doctor is is the product of all of this history of scientific method. He comes down and he gives you this pill, for 3,000 years of medicine, the good, the bad, the ugly, right? The trial and error, all you want. They give you this pill and say, trust me, this will heal your headache. This will heal your diabetes. This will heal your whatever. And you take it. Same exact thing. This is the story of certainty in mathematics. This is point number one. I go back to the table to make the point, to show you. Point number one, I want to remove certainty from the equation. Both mathematics and physics are not certain. They are up to us. We check for validity. We are fallible. Therefore, there is no way I can trust the work of any human being. If it is up to the mathematical community to check for people's proofs, it is up to the scientific community to check for people's proofs in science. Same exact methodology. I will leave room for your questions now. Just about point number one, if you please. So, and I want to hear if people have other opinions, of course.
Well, I think that's really nice. I mean, I like it's the element, it's the sense in which mathematics is like physics. The proof becomes the thing, and it's the proof itself becomes the thing that might be wrong rather than the theory, right? I mean, Newtonian mechanics, Newtonian gravity makes wrong predictions. Well, maybe I should say, when I say that it makes wrong predictions, we've agreed on the fact, like for instance with Mercury, we've agreed on what Newton says Mercury's orbit should precess, and we observe that it doesn't. And so Newton is wrong. Well, maybe we didn't measure it right, or maybe we didn't calculate what Newton's theory says. And I know I haven't checked either of those things. Both the measurements and the theoretical prediction using math and Newton's laws are incredibly complicated. And I'm taking people's word for it that they don't agree, and therefore Newton is wrong. And so in a sense, that's I mean, I really do like that even in math, you have that community, the consensus of the mathematical community is all you can really depend on. And I think maybe that's what you're saying.
Of course, and I'm going to even give you more before I go to Wissam's point in chat. I'm a math teacher, right? This is what I do. You're a physics teacher. Okay, you can be a language teacher. You can be whatever you want. In your classroom, you are the authority, essentially. If someone brings you a piece of work, even though it is correct, and it has happened to me, and I'm pretty sure it has happened to you and to every person teaching out there, sometimes you get fooled. You look at work and you say, this work has mistake. And then the student has enough courage to come to you and tell you, I don't think you've corrected my paper in the right way. I think you've made a mistake. And then you start debating, and then you discover your own mistake in the classroom. The student will correct your own mistake as the expert. And then I ask myself, okay, of course, I'm very embarrassed, I'm so sorry, etc. But then I ask myself, how many students are too shy to ask me whether I miscorrected their papers? How many write proofs that had brilliant ideas, I was just too classical not to see? And then in that classroom, I am the scientific authority, I am the community, right? But even if you bring 10 mathematicians and they look at this paper and they didn't find the mistake, or they found a mistake that is not there, both false positive and false negative, what happens? Nothing. It's their word, right? It's their word that will go. And if you keep generalizing, then you will reach to the entire scientific or mathematical or physical or whatever it is the domain that we are talking about. And of course, the more you get complicated in nature's phenomena, the more different opinions you will find. So if you go, for example, to neuroscience, or if you go to psychology, or if you go to sociology or to politics, you will see experts fighting to death because they have different outlooks. And it doesn't mean that those outlooks aren't quote unquote valid in certain frameworks. It just means that science hasn't developed quite enough to be, I'm running ahead of myself here, as stable as the system we're dealing with, which is the mathematical system. Enough about this. I'm gonna talk about this later. But of course, if you imagine this small example in the classroom and you generalize it, I think it's the exact same thing happening.
It does strike me, though, that I mean, the difference that I see between math and physics, for instance, is that in math, the lack of certainty comes, I think, only from the fallibility. You have these premises, and they do lead to certain deductions if the proof is right, and that's at the end of the story. In physics, the deductions based on the model can be exactly right, but it may not agree with reality, because it turns out it's not because you've made a mistake.
Oh, we're gonna get
Other
there.
than the fact that your model is wrong. Yeah.
Yeah. I'm gonna get to the measurement bit where the stuff that is error in the experiment and error in whatever. It's coming. Wissam, rebuttal to point one. Many domains in life share this quality. This is not an argument for equating them. Absolutely, 100%. This is just one row in my table, right? So this is point number one. People believe that mathematics is absolutely certain, and that's how they will differentiate it from doing physics or other sciences. I'm saying point number one fails for now. Of course, this is not by its own an argument to equating them, but hopefully by the end of today, it will become a little bit more close